Hello everyone, today we'll talk about the problem valid parenthesis string. Here we're given a string consisting of opening and closing parentheses, as well as wildcards, so those asterisks. And those asterisks can be either an opening parenthesis or a closing parenthesis, or perhaps they can disappear if we choose to disappear them. And our job is to create a valid parenthesis string. And if it's not possible, then to say it's not possible. Well, we just have to say if it's possible. We don't have to actually construct it. This problem may sound simple, but I would say it's deceptively simple. And one thing that can perhaps scare us a bit is the fact that the length of our string is up to 100. So if you're not given the limits, you might perhaps try to solve this problem with a greedy approach, something linear, and it might turn out that the solution is not linear, but something much slower. However, in a plot twist, it's actually of course possible to solve this in linear time, but I'd say it's not trivial. Of course, this problem is a parentheses problem, so you probably will be thinking about stacks, perhaps representing those stacks as single numbers, since we have only a single type of parentheses. And you might either try to go a greedy route, as I said, but perhaps you might also want to go safely, without any observations or ideas, and to try, let's say, dynamic programming, or perhaps just a recursive algorithm with memoization, which is essentially the same thing as dynamic programming, just top-down, not bottom-up. And when it comes to dynamic programming, the one thing to notice in this problem, and in many problems concerning it themselves with parenthesis strings, is that if you progress from the left, and you have a prefix, then the only thing you care about on this prefix is if it's correct. And of course we want correct prefixes, so that will be a given, so it has to be okay. And the one thing you care about is the current balance. So essentially, whenever we have a situation like this, we can have essentially a dp of position, so that is the position of the rightmost element, and of balance. And probably during the operation of your algorithm, you can drop the first dimension if you're going left to right by single elements. And I'll show you how to do it in this way, and I will also connect it to some greedy approaches. But first, I'd like to talk about how you might end up solving it greedily. So this is an example code, where the idea I'm implementing here is to count opening parentheses and closing parentheses at the beginning. And now, what do we know? We know that if there are more closing than opening ones, then we have to change some of our wildcards into opening parentheses, and we might as well do it at the beginning, so we know how many we have to change into opening ones. Maybe some will have to be changed into closing ones, and in the middle we can just as well choose to skip them. And we'll be skipping all of them except for, so essentially all of them except for those that have to be open or closed. So it's the length of the string minus 2 times the count of open and closed parentheses, because we want to pair them up and skip everything else. And we also have to remember how many we have already skipped, because the things we have above are actually not enough. And let's go quickly through the algorithm, because it's not the best solution to this problem. We'll maintain a standard count, so this is the size of our imaginary stack. And now, when we encounter a wildcard, if we know it has to change into an opening parenthesis, then we do so for the first WC open counts. And else we skip them and remember that we skipped it. And if there is nothing more to skip, then it has to be a closing parenthesis. And then we progress normally. So open parenthesis, we increase the count. Closing parenthesis, we decrease the count. However, there is also one thing that you have to remember, and perhaps on paper it would be difficult to remember or to actually even imagine this situation. Of course, it's that when you see a closing parenthesis and your count would drop below 0, so your string will be bad, but you have already skipped some wildcard before that you didn't turn into an opening or closing parenthesis, and now you can retroactively imagine that you actually didn't skip it and turned it into an open parenthesis, and everything is okay. And in that case, you also have to remember, and it's also easy to forget, that later when you have to skip another wildcard, since you now created another opening parenthesis in this place retroactively, you have to create a closing parenthesis at some point at the end. Of course, if that's not possible, you return false as normal. And let's say at the end, if the count is 0, and also there is nothing more to skip, because in that case, this number could be negative, such that we essentially try to make sure that at the end we create another closing parenthesis, but it's not possible. And if those things are okay, then the whole answer is okay. Okay, but that's awful. And we want to find out if it's possible to solve this problem in an easier fashion. So one thing we can notice, which is a common idea when it comes to greedy algorithms, though good luck proving it when you're asked how to prove it or if it actually works, is to go in one direction and then be extremely greedy, just always make the same decision, and go backwards and always make another decision. And if both of those passes are okay, it might turn out that the whole problem is also solvable. And such is the case in this case. So essentially we go from left to right and we treat everything that's not a closing parenthesis as an opening parenthesis. And if you at any point we see that the string cannot be valid, so essentially we treat every asterisk as an opening parenthesis. And if we see that the string cannot be valid, we say it's wrong. And then we do the same thing, but in reverse. Now we want all of our parentheses to be closing parentheses, and also if it's not possible, we return false. And it turns out that in this case, if both of those passes are okay, then the answer is true. You might imagine that they are essentially meeting in the middle, because one of them can have too much opening parentheses from the left, one can have too many closing parentheses going from the right, and there is possibly some way for them to actually negotiate the number of parentheses and to create a correct solution. And as it turns out, this idea is actually quite nice. So let's see right now our dynamic programming. So as I mentioned, this can be solved with dynamic programming, and the good thing about this type of solution is that you actually don't have to have too many good ideas. You just essentially notice what we said before, that you have an index that you're interested in, so this is an index of a prefix of your string, and you also have a balance for an index ending at this position. And if you have for every balance, you have a new letter here, and for every and you want some balance at this position, then you're interested in essentially balance +1, balance -1, perhaps the same balance starting before. So if you have all those things calculated before, then you can just use them to answer if it's possible for your current prefix. And essentially you can write it like so. In Python, memorization is very simple because you have the cache decorator. And now, if index is less than 0, so there are no more letters to use, then we just have to remove that. We have to answer if just the balance is 0. Because it's possible to achieve a balance of 0 without using any characters, and it's not possible to achieve any other balance. Then, if balance is negative at any point, well, it's impossible to have a good string that has a prefix with negative balance. Otherwise, we have a character at this position. If this is a standard character, so it's an open parenthesis, in this case we see if it's not a closing parenthesis, but if it's an opening parenthesis, we have to add our prefix, get a balance that's 1 smaller, because after adding this parenthesis, our balance will increase by 1. We're being asked for balance, so before the balance had to be 1 less. The same for a closing parenthesis, the balance had to be 1 more because now we closed another parenthesis. And both of those apply. For instance, this one applies for an opening parenthesis or a wildcard. This one for a closing parenthesis or a wildcard. And also we can of course choose to skip a wildcard. In that case, balance stays the same because this character has just disappeared. And in that case, we just ask if we can go through the whole string, so starting by its last letter, and get a balance of 0. And now probably the most beautiful and most important observation of all. Because if you, for instance, look at this greedy solution and you think about what it means for those two left and rightmost solutions to meet at the middle. If you look at the dynamic programming solution, where you see that essentially at any point where you're, let's say, at some balances, then you maybe go up one, maybe go down one, and you also are interested in those ones. What you're essentially maintaining is the interval of balances that are achievable for a given prefix. And at the end, of course, this has to be exactly 0, right? Because in this one, we are trying to get our interval, let's say, the upper edge at the beginning and the lower edge going going backwards, going from the right. And if it's not an empty interval, then we're happy. This is, let's say, more explicit in the dynamic programming solution, because we always either go the same or up one or down one, but so an interval still stays an interval. And we can essentially just go from left to right without maintaining anything else and remember what that interval is. And that's probably the most beautiful solution to this problem. So our starting interval is from 0 to 0, because the balance at the beginning has to be 0. And we'll be maintaining what are the possible balances for us to get at a given prefix. So if we have an opening or closing parenthesis, the situation is very simple. Because for an opening parenthesis, the whole interval goes up by 1. So the smallest number of unclosed open parentheses goes up by 1, and the highest number of unclosed open parentheses also goes up by 1. Same thing with closing parentheses. Our highest number goes down by 1, and our lowest number also, although our lowest number never can be negative, because it's impossible to have a valid prefix that is negative. Of course, the interesting part happens with wildcards, but in this case, if we treat the wildcard as an opening parenthesis, we can increase our highest. If we treat it as a closing parenthesis, we can decrease our lowest. And anything else still falls within our interval, so we don't have to think about it. So our interval just grows up and grows down. If at any point our highest is less than 0, that means that we have encountered so many closing parentheses that even by treating all the wildcards as opening ones, we cannot make a valid parenthesis string on that prefix. And otherwise, we just have to make sure at the end that our lowest possible number of unclosed open parentheses is exactly 0. Right? And it might be a little bit, let's say, surprising that it actually works. That, for instance, but of course it cannot be negative. And also, if you use a wildcard, you can skip adding it. So it turns out that you can just maintain this interval explicitly by its left and right end. And at the end, we just want to make sure that 0 is within this interval, but since our interval never goes negative, then we just say that the lowest point of our interval is actually equal to 0.